Hello and welcome to the Unit 2 Section 4 video on proofs. So we're going to start off by talking about algebraic proofs, and by talking about algebraic proofs we're going to be able to discuss how we can prove things mathematically. Algebraic proofs are a little bit easier way to start before we jump into geometric proofs because they're a little bit more linear. So algebraic proofs, we're starting with what a proof is. So a proof is an argument that uses logic, definitions, properties, and proven statements to prove a conjecture is true. Remember, a conjecture is something that we conclude based on some other given information. Each statement in a proof must fit in logical sequence with what is previously stated or given, and it must have a reason to support it. So if you've ever solved an equation in algebra, you've already done a proof. You just haven't explicitly listed down the steps that you took to solve the problem, but those steps are there in your head. They are things that you have already learned, and they are things that you almost do second nature now. So here's a list of the properties of equality. This is a review from algebra, and what I suggest you do is when we do these algebraic proofs, refer to these properties. This is just kind of all the properties in one place that you can use as you move through each step of solving an algebraic equation. So you have the addition, subtraction, multiplication, and division properties of equality. That essentially says if you add, subtract, multiply, or divide something to one side of an equation, you have to do it to the other. The reflexive property simply states that A equals A, so anything is equal to itself. The symmetric property, if A equals B, then B equals A. Okay, so you can flip what's on either side of the equal sign. Transitive property, if A equals B and B equals C, then A equals C. We briefly mentioned that in the last section when we talked about deductive reasoning because it's very similar to the law of syllogism. The substitution property, if A equals B, then B can be substituted in for A in any expression. The distributive property, if you're multiplying A by the quantity B plus C, then you multiply A by both B and C within that parentheses. The commutative property, A plus B equals B plus A, and that goes for multiplication as well. A times B equals B times A. So as you have learned, if you start with a true statement and each logical step is valid, then your conclusion is valid. An important part of writing a proof is giving justifications to show that every step is valid. So the way we're going to do this and the way we're going to organize it is by using a two-column proof. And a two-column proof is a common way to organize it. The first vertical column will have your statements, so for example the steps to solve a problem, and the second vertical column gives you the reason for each step. I like two-column proofs because they are easy to organize, they're easy to follow, especially in algebraic proofs. The other types of proofs include paragraph proofs, where you can just write the proof in paragraph form, where you give each step and you state what the reason is, and you do this all in sentences. But I think a two-column proof is going to be best for what we're trying to achieve here. So let's do an example of one. So the first step you're always going to have is a given. Okay, we're starting with this equation that we have to solve for x, and we want to prove that x equals 18. Notice that we're given the answer here. We're not really concerned about what the answer is. We are concerned about how you get to that answer, and you have to justify every step along the way as to what you do. So first thing we're going to do to solve this problem is we're going to multiply the 3 by the 2x minus 5. That's going to give us 6x minus 15 equals 4x plus 3 minus 9x. And what we did here was the distributive property. Okay. Now, as we move on down, we're going to combine the like terms here. Okay. So all of this is stuff that you did back in Algebra 1. So 14x minus 9x gives us 5x. And our reason is not going to be stated as combined like terms. our reason is going to be is substitution. What we did was we substituted one value for another. So the substitution property. So explicitly what we did was we substituted 5x in for 14x minus 9x, because those two things are equal to each other. All right, now we're going to subtract 5x from each side. And in doing so, we used the subtraction property of equality. And then we are going to add 15 to each side. And that was the addition property of equality. And that concludes this proof. So this is a simple algebraic example. Let's throw in just a touch of geometry. So for this one, we are going to fill in the reasons column for our two-column proof, and we're going to write down what we're doing here. So we have a segment here, okay? And what we're going to do is prove that n equals 5. So to do this, we're going to write down our given. Well, our given is PQ equals 3n, because that's given in the segment. We're given that QR equals 25, and then we're given that PR equals 9n minus 5. And this is all of our given. Remember, we always start with our given. All right, so now in our next step, we're going to state that PQ plus QR equals PR. That's something that we learned last unit. Because anything that we learned in the previous unit is fair game, and that's the segment addition postulate. Okay? Now, we're going to take each of these items that we have in our given, and we're going to substitute them in. So we get 3n plus 25 equals 9n minus 5. And we did that by substitution. Now from here, we're just doing an algebraic equation. So we're going to subtract 3n from each side. And doing so, we used the subtraction property of equality. And then we're going to add 5 to each side. And that was the addition property of equality. And now we're going to divide each side by 6, which gives us 5 equals n. And we did that by using the division property of equality. And then finally, this is not the same as what we're out to prove. What we've got to finish with has to look exactly the same as what we're trying to prove. So we're going to flip it, and doing that, we utilize the symmetric property. And now our proof is complete. So I want to share just a few tips for writing a two-column proof here. You want to number each step. The most common reasons are given, postulates, theorems, properties, or definitions. And we're going to be getting into some more theorems here shortly when we get into geometric proofs. You want to start with the given information, draw a picture if necessary, and label it with the given information. Every statement must have a reason. And then finally, the final statement in the proof should match exactly the statement that you are trying to prove. So let's do one more example before we move on to geometric proofs. So for this one, we are going to write down our given. So just like before, jk is x plus 32. KL is 3x plus 51. And JL is 23. And that's our given. Now for number 2, JK plus KL equals 23. And you'll notice this is very much how we started the last one. As you do more proofs, you're going to start to see themes, things that look familiar. And that comes with just doing practice. All right, for number 3, we're going to substitute in. So we've got x plus 32 in for the jk. We're going to have 3x plus 51 in for the KL. And then 23 here. And that's substitution property. Now we're going to combine like terms. Now we're going to combine everything that's on this left-hand side at the same time because we're going to use substitution twice, but since we're doing it all in the same step, then it's fine. Okay, so we're going to do 4x plus 83 equals 23. And here we substituted. And now we're going to start moving things. So we're going to subtract 83 from each side. That gives us 4x equals negative 60. That was the subtraction property of equality. And then finally, for the last step, we're going to divide by 4. And that gives us x equals negative 15, which is what we were set out to show. All right, so this kind of gives us an idea of how proofs work. Remember, algebraic proofs are far more linear than when we get into outright geometric proofs, which is what we're about to try now. So when you're doing a geometric proof, you're going to use deductive reasoning to create a chain of logical steps that move from the hypothesis to the conclusion of the conjecture you are proving. So remember, deductive reasoning, you have to use rules and laws to justify your reasons and your conclusions. Okay? Unlike inductive reasoning where you're making assumptions. By proving that the conclusion is true, you have proven that the original conjecture is true. So when writing a proof, you're going to follow from the hypothesis, you're going to go through all the definitions, postulates, properties, and theorems that you need to reach your conclusion. It is important to justify each logical step. Recall, congruent segments have equal lengths, and congruent angles have equal degree measure. So the reflexive, symmetric, and transitive properties can port over very similar to what you had in algebra. The reflexive property, symmetric property, and transitive property all work for congruency as well. Now, a theorem is a statement that you can prove. Once you have proven it, then you can use it as a reason in proofs. So let's talk about a few theorems that are going to be useful for you as we work through these. We have the congruent supplements theorem, which basically states that if you have, say, for example, I'm just going to skip the definition here. You can read it for yourself, but I think it's better served in an example. If the measure of angle A plus the measure of angle B equals 180, and the measure of angle C plus the measure of angle B equals 180, the only difference here is A and B, or A and C rather. So therefore we can say angle A is congruent to angle C. Same thing for complements. Okay, if the first two angles equal 90 degrees, and the third and second angle equals 90 degrees, then the first and third angle are congruent. So it works for both of those. The linear pair theorem states that if two angles form a linear pair, then they are supplementary, which that just comes directly out of the definition for a linear pair. Okay, if they form a linear pair, they are supplementary. That's just part of being a linear pair. The right angle congruence theorem states that all right angles are congruent. So it doesn't matter where your right angles are, they're all 90 degrees. So therefore they're all congruent. Unlike algebraic proofs, geometric proofs are not always linear in their steps or statements. Sometimes you have to jump around to find your evidence, and you're going to see that in the examples that we are going to do here. There is also not always one way to write a proof. Some steps may be reversible, so your proof and another student's proof may be different, but still come to the same conclusion, and both still be correct as well. So let's go through the rest of these examples, and you're going to see how this works. So for example 4, we're going to fill in the reasons column in this 2-column proof. So given that the angle 4 is congruent to angle 3, so we are told that angle 4 is congruent to angle 3, we are going to prove that angle 1 and angle 2 are congruent. So as always, you're going to start with what you're given. You're just going to write it down exactly the way it is. Okay? And the reason here is it's given. So if we know that the angle 4 is congruent to angle 3, we know that the measure of angle 4 is equal to the measure of angle 3. And that comes from the definition of congruent angles. Or if you just want to say definition of congruence, that's fine too. Okay? Now, let's see what observations we can make from here. Well, we know that 1 and 4 form a linear pair, and 2 and 3 form a linear pair. So we're going to say that angle 1 and angle 4 form a linear pair, and the same can be said for angles 2 and 3. Okay, so we use the definition of a linear pair for our justification here. Definition of linear pair. All right, so now if we know that 1 and 4 form a linear pair and 2 and 3 form a linear pair, then we can say that the measure of angle 1 plus the measure of angle 4 equals 180. And we can also say the measure of angle 2 plus the measure of angle 3 equals 180. And that comes from the linear pair theorem. All right, and then for number 5, we're going to take what we already stated in 2, that measure of angle 4 equals the measure of angle 3, and we're going to substitute that in. So I'm going to keep this first line the same, and let's substitute that into the second line. And here we use the substitution property. And then finally, since we know that everything's the same except for 1 and 2, we're going to use the congruent supplements theorem to show that angle 1 is congruent to angle 2. And that comes from the congruent supplements theorem. Okay, so hopefully you kind of get a sense of how this works. Now, you'll notice that we did jump around a little bit. We started with what was given and we kind of went with what we could off of that. Then we looked at the figure and wrote down what we knew, and then we came to some conclusions out of that for number 4. Then we used 2 and 4 together to get number 5, which led us to number 6. So you see we jumped around a little bit. We had to use 2 and 4 together to get to 5. But you'll notice that 5 has to come after 2 and 4. Now, could we have done 3 and 4 a step earlier and then done 2 after step 4? Yes, we could have. So there is a little bit of play in what order that these things go in, but certain things have to be after other things because they are conclusions from previous statements. So let's look at example 5 now. So we're going to provide a 2-column proof for the following. We were given this information that angle 1 is congruent to angle 3, and we are given the figure here, and we're going to show that angle 2 is supplementary to angle 3. Okay, so what we're going to do is we are going to start with our given. Angle 1 is congruent to angle 3, and we know from that that the measure of angle 1 is going to be equal to the measure of angle 3 because of the definition of congruent angles. We saw that in the last example. Again, themes are going to repeat themselves as we move along. So the more you do proofs, the more you'll have an idea of where to go. All right, that's all we can really get off of our given. So let's take a look at our figure. Well, we know that angle 1 and angle 2 form a linear pair. So we're going to state that as our next statement. Angle 1 and angle 2 form a linear pair, and that's from the definition of a linear pair. Okay, we can observe that right here in the figure. Then we're going to take this and put down what we know from that. Well, we know that the measure of angle 1 plus the measure of angle 2 has to be 180 degrees since they're a linear pair. That comes from the linear pair theorem. The two angles are supplementary. Then we're going to take what we know from step 2. We're going to take the measure of angle 3 and substitute it in for the measure of angle 1, and that leads us to measure of angle 3 plus the measure of angle 2 equals 180 degrees. And that's the substitution property, and we pulled that from number 2. Okay, sometimes it's good to just make a note of where we're substituting from, which step. And then finally, if the measure of angle 3 plus the measure of angle 2 equals 180 degrees, then the measure of angle 2 must be supplementary to angle 3, and that comes from the definition of supplementary angles. And we are finished with this proof. All right, let's head on down to the next example. Example 6, we are going to provide a 2-column proof for the following. So I'm going to go ahead and pull this up. Angle 1 and angle 2 are supplementary. That's information that we are given. We are going to prove that angle 2 and angle 3 are congruent. So we start with what we're given. And since they're supplementary, then we know that the measure of angle 1 plus the measure of angle 2 has to be 180 degrees, given this definition of supplementary angles. Now we're going to go to our figure. Well, we know that 1 and 3 form a linear pair, so we're going to put that as our next step from the definition of linear pair. And since 1 and 3 form a linear pair, then the two have to add together to give us 180 from the linear pair theorem. Remember, we have to give a reason for everything that we write in the statements column. Now, since the measure of angle 1 plus the measure of angle 2 is 180, and the measure of angle 1 plus the measure of angle 3 is 180, then we know that angle 2 and angle 3 are congruent, and that comes from the congruent supplements theorem. And that is using steps 2 and 4 to reach that conclusion using this theorem. And that's it for that proof. All right, moving on to example 7, we're going to provide a 2-column proof for what's given here. We have our figure, we have our given information that angle 1 and angle 4 are congruent. So we start with our given. And this time we're not going to talk about the measures because we're not going to anything that is a measure, okay? So we're going to cut out a couple of steps here because we don't necessarily need the measures because we're not going to talk about anything being supplementary or complementary. Because what do we have here? We have vertical angles. That's something that I observed here. 1 and 2 are vertical angles, 3 and 4 are vertical angles. And we know that vertical angles are congruent. So therefore, angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. The reason being, vertical angles are congruent. Now what I'm going to do is use what we're given in step 1, and we're going to substitute. And I'm going to substitute in that angle 4 in for angle 1 here. So we're just going to put angle 4 in at the beginning here, and we're going to use substitution property to do that. So now we have angle 2 is congruent to angle 4, and angle 3 is congruent to angle 4. Well, if we read it this way, angle 3 is congruent to angle 4, and angle 4 is congruent to angle 2, so therefore angle 3 must be congruent to angle 2, or in other words, angle 2 is congruent to angle 3. And we use the transitive property to achieve that. And that concludes the proof for this one. So this one only took 4 steps, and that includes the given. All right, moving along to example 8. This one, you're going to see a lot of similarities to what we did in the previous one. So we have angle 2 is congruent to angle 3, so we are told that these two are congruent. We're going to show that 1 and 4 are also congruent. And once again, we have vertical angles here. So I'm going to make that observation. Angle 1 is congruent to angle 2, angle 3 is congruent to angle 4, because vertical angles are congruent. Now I'm going to substitute in angle 3 in for angle 2 here. And I think this is going to make the transitive property that follows look a little more straightforward. If angle 1 is congruent to angle 3 and angle 3 is congruent to angle 4, then angle 1 and angle 4 must be congruent. And that comes from the transitive property. All right, let's take a look at example 9. We're going to provide a 2-column proof for this. I'm going to scroll it up just a little bit so we have enough space. So ray BD, which is right here, bisects EBC, which is this angle. So if this ray bisects this angle, then we are given 2 equal angles, that being angle 1 and angle 2. Angle 1 and angle 2 are congruent because of the bisection. So that's the definition of an angle bisector. Angle 1 and angle 2 are congruent. And if they are congruent, then the measures must be equal, which is from the definition of congruent angles. And that's everything that we can do off of what's given. So let's look at our figure for more observations. Well, let's look at what we're trying to prove. We're trying to show that 1 and 3 are supplementary. So we want to get something with angle 3 in the mix. So let's look at our figure and see what observations we can make about angle 3. Well, here's a straight line, and 3 makes that linear pair with angle 2. So let's say that angle 2 and angle 3 form a linear pair, and that's from the definition of a linear pair. If they form a linear pair, then their sum must be 180 degrees, and that's from the linear pair theorem because they're supplementary. Now we can take information we have from 3 and substitute it into 5. So we're going to substitute angle 1 in for angle 2. So now we know that the measure of angle 1 plus measure of angle 3 is 180 degrees, and we did that from the substitution property, and we pulled that from number 3. And then finally, if measure of angle 1 plus measure of angle 3 is 180 degrees, they are supplementary, which is what we were set out to prove. And finally, example 10. We're going to provide a 2-column proof for this figure showing that angle 1 and angle 4 are complementary. So we want to show that 1 and 4 are complementary, and we're told that FEC is a right angle. So we're told that's a right angle, which means 1 and 2 together have to add to give us 90 degrees from the angle addition postulate. Okay? Then angle 2 is congruent to angle 4 because we know that they are vertical angles. That is what we just see here because we want to get to angle 4 somehow. So we find some sort of relationship that involves angle 4, and that is that 2 and 4 are vertical, so therefore they are congruent. If the angle 2 and angle 4 are congruent, then their measures must be the same. That comes from the definition of congruent angles. And then next, we're going to use substitution. We can put angle 4 in for angle 2. So the measure of angle 1 plus the measure of angle 4 must be 90 degrees. That comes from the substitution property. And if that's the case, then angle 1 and angle 4 must be complementary. And that's from the definition of complementary angles. So that completes this section of the unit, and that actually completes Unit 2. So we've talked about proofs, and really the best way to get good at them is to get practice at them and to see what kinds of themes pop up that are similar for different situations, okay? It's very important that you know your theorems, your definitions, your postulates to be successful in doing geometric proofs. And we'll continue to do proofs as we move forward through the following units.